This is W naught, and this distance is L by 2, and this distance is L by 2. Easy. So this sort of problem is easier in the sense because we can see that we don't have to solve the whole problem because it's a symmetric problem. Exactly same situation right in the middle. The forces, reactions, beams, lengths, everything is exactly the same. So we will just solve half of the problem like this. But before we do that, we know this there are two reactions. And those reactions will be equal. There's no change. Both R1 and R2 will be exactly the same. And we can find out those reactions, or those have to be found out before we move further. So R1 must be equal to R2 using symmetry. We are using symmetrical problem, and what that should be? Anybody? If we use symmetry and use R1 equal to R2, what would be that? What should be R1 and equal to R2 using symmetry? It's a symmetrical problem. Come on, guys. You should be able to answer this. What's the half load? You just take the half of the load. This is a triangular load. So it will be half of the base times height. 1/2 base. Base is L by 2. And this is 2. They will both will be exactly the equal.
L by 2.
Yeah. L by 2 times W naught. Although if we want to compute the whole force, that's fine. The total load is W naught times L, and that must be equally divided between these two supports. So half will be borne by this, and half will be borne by this. So we exactly know this is 1/4 W naught. Both R1 equal to R2. They both have this load. So R1 is equal to 1/4 W naught, and R2 is equal to 1/4 W naught. No, L, W naught L, and W naught L. L is there as well.
सर ये दोबारा समझा दें.
Okay. So let's look at it. What's the total load? So the total load. What's the total load? We can although we can solve for the total load and divide, because we know this total load is supported by these two supports, R1 and R2. So exactly half of the load will be on this support, and half of the load will be on this one, because there's nothing different. The distances are same, the loads are same, so we can think of that. So we just use symmetry. We divide the problem right in the middle and solve, okay, just one part of it. So R1 will be equal to R2. So we just need to find out what is this total load. This is triangular load, so I just use 1/2 base L by 2 times height W naught. So R1 equals R2 equal to half base height. So this R1 equal to R2 1/2 W naught L. So R1 is 1/4 W naught L. R2 is also equal to 1/4 W naught L. And now I can take a segment somewhere here. Let me redraw it. And this distance is X as usual, although our complete segment is like this. So we're solving this segment. And similar, so the force would be equal to what? If I need to find out V, Now we have two forces. One is the R1 and one is the triangular load. So sum of the forces in the y direction on the left side of the segment, that is our definition of shear force. One force is R1. This is acting vertically upward, so this will be positive. The other triangular force is acting downward, so that will be negative. That will be 1 over 2. Base is x, and height. How much is height? Again, we have to think. Same trick we can use always. Using a larger triangle, the ratio of the larger triangle is W naught over L by 2. This must be equal to ratio of this smaller triangle, which is y over x. So y will be equal to W2 W naught L over 2W naught x over L. So I'm going to write 2 W naught x over L. R1 is equal to 1 by 4 W naught L minus 2 will be cancelled out, minus W naught over L x squared. That is our relationship for B. Are we good?
Yes.
Yes, sir.
Well done.
Sure.
So let me, before I move to the bending moment, let's take the diagram. So if I put x equal to 0, this will become 1 over 4 W naught L. This will become 0. When I take shear force at x equal to L by 2, half of this distance, this will become 1 over 4 W naught L minus W naught over L and L by 2 square. Let me erase all this. So this would become 1 over 4 W naught L minus W naught over 4 L. Same. So they'll become 0 in the middle as well. So we need to take at least one more point right in between these 2 points. But that can be adjusted. So because this force will continuously vary, whatever the direction we will have on this side, exactly same diagram in the opposite side will be done for the other side as well. Are we good on this?
Yes, sir.
So I'm going to take the bending moments. The bending moment will be again R1 times X, R1, and minus force, whatever the force is, time, how much? How much is the distance? X over 3?
X.
X over 3, 1/3 of the X, because this distance is X, so whatever the distance we take, that's 1/3 of the X. So R1 is 1 over 4 W naught L minus force. Force was W naught over, what was the force?
W naught divided by
W naught divided by 3, I think.
no sir L W naught divided by